Great, thanks. Hi, everybody. I'm Colin Ryan Chandler at University of Washington. I'll be your moderator for the entire day. Actually, it's just a couple sessions. I broke my wrist and my thumb trail running fall, because that's what I'd want to know if I saw me standing up here. Um, Great, and so we are joined first by Kat Volk from Planetary Science Institute. Looks like we're good to go. And they need a moment, so we'll do a dance. No.
All right, great. Sound okay? Like hook my microphone on the.
I couldn't hear you. Could they hear you in the back?
Oh, and is there a way to get the slides up on the computer here too, or is it just? It's all right, it's fine. Okay. So I know this is a rocky small bodies session, but I'm actually going to mostly talk about icy small bodies. But if ice is low enough temperature, it's like a rock, so that counts. And what I'm going to focus on today is kind of some broad brush stroke stories about the connected icy small body populations, ranging from the metastable long-term reservoirs, the Trans-Neptunian populations and the Oort cloud, to the transient and constantly replenished JFC and Centaur populations, and how the stories of these populations are kind of related to things we might be seeing in other planetary systems and what they are telling us about the history of our own planetary system. So we're going to start from kind of telling the story of our solar system, because we started when the planets formed. They of course did not form in the configuration we find them today. And all of these icy body reservoirs are what's left over of the massive planetesimal disk that formed kind of outside of where planet formation in our solar system stopped. So we had our giant planets forming in a more compact configuration, perhaps with an extra ice giant. And then they interact with this massive planetesimal disk and create the populations we see today during the epoch of giant planet migration. So what we have left today are the Trans-Neptunian populations and the Oort cloud populations that then refeed into the inner solar system. So we're going to start kind of from the outside in. The scattered disk and the Oort cloud populations formed during the epoch of giant planet migration. And of course, we don't have any direct observational measurements of the Oort cloud itself, but we have all the long period comets that come in from the Oort cloud. And there are actually some prospects, maybe. I know people are looking into occultation studies to try to perhaps get some direct constraints on the Oort cloud. But what we've got over here is a model population from one of Nate Cabe's simulations, where he does the whole kind of start to end planet migration. And this is what the scattered disk and Oort cloud look like. When you model the epoch of planet migration, you scatter a bunch of things out from that massive primordial disk. You can see, so this is perihelion distance versus semi-major axis, and this is a log scale going from the planetary region out to the edge of the Oort cloud here. So you can kind of see the scattered disk population, which has perihelia close to where the giant planets end today. So Neptune's at 30 AU today. So you have some population here that have perihelia focused in the planetary regions. That makes sense. They got scattered out by the planets. And then, of course, the objects that get scattered out far enough are then affected by external perturbers. So we can kind of look at what the present day dynamics of these really distant populations looks like. And this is a very nice schematic from Mellon Salenfest, showing, again, in perihelion on the y-axis and semi-major axis on the x, we've got a bunch of different dynamical processes going on affecting these populations. So in the outer regions, once you're past today, roughly 1600 AU, if you are not strongly coupled to the planetary region, meaning your perihelion distance is not really planet approaching, the dynamics are dominated by galactic tides. You can also have passing stars and other things that are happening. So the dynamics out here are dominated not by the solar system itself, but by external perturbations. You can get a mix of both external and internal perturbations at lower perihelion. When you are more tightly bound to the sun at lower semi-major axes and low perihelion, you're dominated by those kind of direct interactions with the planets. And even closer in, you get both direct interactions through scattering, but also mean motion resonances and other direct planetary interactions there. So what's interesting about thinking about this is that this is the snapshot of kind of where these boundaries are today, but this is not where the boundaries always are. Even in the current solar system, as the sun is making its way around the galaxy, these boundaries can shift around. You can move kind of the trade-off between planetary interactions and galactic tides, sometimes inward, sometimes outward. You can have passing stars that can change the distribution of the Oort cloud or the distant scattering populations. And of course, when the sun formed and it was in its birth cluster, you had the cluster dynamics to deal with. So what's kind of fun about the distant part of the scattering population in the Oort cloud is that it's not just recording what's going on in today's solar system and today's galactic environment, but it also has some sort of record of what was going on in the early solar system. So if we look at this nice schematic from one of the Comet's 3 chapters, we had the sun forming in its birth cluster, you have planet formation, you have the era of scattering out of that massive planetesimal disk as the planetary system is kind of taking on its modern form. And so we're over here, but a lot of different things could have happened over here when the solar system was still interacting with its birth environment. So some kind of open questions from this. One question, when did the formation of the scattering population and the Oort cloud happen relative to the sun's evolution within its birth cluster? So that birth cluster dispersed on some time scale. The sun is not in a cluster today. But what was the timing of the major scattering events of planet migration relative to that birth cluster time scale? And that's relevant, and I couldn't embed movies in the PDF, but Hal Levison had a nice paper, I think, in 2006, showing that if Oort cloud formation happens early enough, you can trade basically scattered planetesimals with other planetary systems. So if Oort cloud formation is very common and it happens early, then we could have exocomets in our own cometary reservoir in the outer solar system. So our own solar system kind of depends on how common this mechanism is. And then, of course, the other thing that has come up kind of periodically, and there's been some work on it recently, is what is the role of stellar flybys in shaping both the Oort cloud, and we're going to come to the closer in trans-Neptunian populations, but even those close in TNO populations. How many stellar flybys have we had in the solar system's history? Is it affecting the distribution of TNOs that we see today? So these are all things that are outside of our solar system but leave an imprint on the populations within our solar system. So now we're going to come in a little bit closer to the trans-Neptunian populations. So again, we have perihelion distance and then inclination versus semi-major axis. And note that the right panel is just a zoomed out log scale. So you can see, these are observed objects, and we go out to, I think 1200 AU is kind of the most distant TNO, perhaps maybe inner Oort cloud. It's kind of debatable object that we've observed directly so far, besides the long period comets. But we see kind of a lot of rich dynamical structure here. These are the Gladman style classifications. So classical objects are things that are on at least 10 million year stable orbits that are at low eccentricities, and they're focused kind of between 35 and 50 AU. The scattering objects are actively changing their semi-major axes on short timescales, 10 million year timescales. Detached objects are sometimes changing their semi-major axes on slightly longer timescales. Sometimes they are truly, giga-year stable on their orbits. And then, of course, my favorite objects are the mean motion resonant objects, which I will not talk quite as much about as Sam thought I was going to talk about yesterday. But if you have any interest in resonant objects, you can chat with me. I have lots to say. So kind of the big picture idea from these TNO observations have led us to this kind of schematic view, and this is very simplified, of what the TNO populations look like today. So broadly speaking, we can divide them into creatively named cold and hot populations. And these are, dynamically motivated. So the cold belt is currently very confined radially. These are objects on nearly circular, nearly coplanar orbits. They are physically distinct. We now have color data, spectra data that show they have distinct compositions from the rest of the TNOs. They have a lot of wide binaries. There's evidence they have not undergone a particularly large amount of collisional evolution because of that. So this cold belt is probably the only in situ remnant in our solar system of the original planetesimal disk. We think they formed where we see them today. There's been some jostling about, but that is a remnant population from the era of planetesimal formation. And then kind of overlaid on top of that is everything else, which is the dynamically excited higher eccentricity, higher inclination populations that came from that closer in, more massive planetesimal disk. And kind of some highlights of what we know from our current observational constraints about kind of the numbers for these. And there are some other surveys besides AUSIS that have population estimates. This is just the slide I already had with the most recent population estimates from AUSIS. And kind of the takeaways here, I guess down at the bottom, we have decent estimates for the classical belt, so that 40 to 50 AU region. And there's about twice as many dynamically hot objects as there are dynamically cold objects. And the interesting thing here, they also have the same size distribution, with the caveat that there are no dwarf planet or really large things in the cold population. So the cold population has an upper size limit that probably indicates it was a slightly lower density disk than where the hot population formed, so it didn't form any really large objects. But the new deeper surveys are showing that they have the same size distribution as you go down to smaller sizes. We've got a significant detached population, so that's kind of the higher perihelion portion of that scattered disk that formed during the era of planet migration. It is pretty numerous. This is the least well observationally constrained population because they have a closest approach to the sun that is pretty far. So we don't detect them as often as the things that come in closer. So there's a huge asterisk on this particular population estimate because it is a difficult population to model. But it's probably comparable in number to the scattering population. And then my favorite, all of these hugely populated resonant populations. These are just the ones we have population estimates for. We have observations of resonant objects in many other resonances besides the ones on this list. These are just the resonances that have enough detections from characterized surveys to make an estimate of the population. So those are kind of the key takeaways. And the really high number of resonant objects is really important for learning about the history of our solar system. So if we look at kind of the big picture, large semi-major axis range, the dominant dynamics of these populations is kind of scattering and diffusing, just interacting with the planetary system, changing the orbital energy. So they kind of wander along in semi-major axis along kind of lines of constant perihelion distance. As they're doing that, many objects can transiently stick in Neptune's resonances as they are wandering around the scattering and detached populations. And that can cause them to kind of wander up and down in eccentricity and therefore in perihelion distance. There are also some stable resonant populations that are captured during the era of planet migration. And those are very important for testing different models of planet migration. And then we do have a limited number of truly like long timescale detached objects like Sedna, like VP113, that they got out to large perihelion, large semi-major axis orbits somehow. And in the current environment, they're not going to change. They're not really interacting with the planets. They're kind of too close in to truly be interacting with external perturbations at the moment. And those are also very interesting because they record something that we don't see today that did happen in the past. So some questions that these distant objects can help us answer. Kind of the biggest one maybe for the resonances is that concept of grainy migration that I think was brought up yesterday in someone's talk or the day before. They blur together. But the planetary migration process was not just a smooth process. The planets are interacting with each other. They're interacting with large objects in the planetesimal disk. And as Neptune is migrating, its resonances move along. And if there are a lot of really big objects in the planetesimal disk, Pluto-sized and larger, interactions with those big objects will cause small jumps in Neptune's migration, and that can strand resonant objects. So there are some ideas that some of the detached populations are kind of resonant dropouts. But you have to preserve the large primordial resonant populations during any process and like that. So you can kind of see that the really high A observations are still sparse. So we're still kind of working on testing those ideas. But these populations should be able to tell us how many dwarf planets were in that original planetesimal disk, which will tell us about the disk formation conditions. The other thing is those stellar flybys again. They don't just affect the super distant, they could have been closer, especially in a birth cluster environment. So like one idea for some of these really high Q detached objects is that they could have interacted with a stellar flyby. There's been some published papers recently saying that you could get a primordial alignment of their orbits that might indicate they had some perturbation event in the past in common. And that could have been ejecting a planet. So we can have rogue planets in the early solar system sculpting these populations. Could have had stellar flybys. There's a lot of other perturbations that wouldn't be present today. And then, of course, the Planet 9 debate, are there unseen masses in the outer solar system that are affecting some of these high Q? Because all the dynamics here are assuming we know about all the planets in the solar system, which that could be untrue. There could be things we haven't seen yet. So again, moving a little bit closer into the classical belt region, the dominant dynamics here are kind of long-term diffusion, kind of chaotic diffusion due to interactions with resonances. So you can see the classical belt objects mostly have perihelia larger than about 35. They're not coming in super close to have close encounters with Neptune. We've got some of these strongly populated resonances that were captured during the era of planet migration. And we have some secular dynamics going on, like this gap in the cold belt where there's no low inclination objects here. That's due to the present configuration of the giant planets. Low inclination orbits there are not stable due to secular resonances. So some things we have made really good progress on inferring, especially from this area of the TNO populations. We know that there's a limit to how excited you can make Neptune as it's arriving in its final orbit, because you have to preserve these really low inclination, low eccentricity orbits. And if you make Neptune too dynamically excited, you will destroy those. There's also this edge in the cold population, and that is a little uncomfortably close to the 2-to-1, but that's a real edge. It's not an observational bias. And that seems to be indicating some real edge in the original planetesimal disk. But that's still a little bit open to debate. So some of the open questions, could that disk have extended out further? You could put a cold disk at 70 AU and we wouldn't quite have seen it yet with our surveys, although we're getting there. So I feel that number will probably change in the next year or two. What is causing this edge? And again, stellar flybys have been one of the options that have been proposed for truncating the disk, because of course in debris disk systems we see disks going out much farther. So our Kuiper belt trans-Neptunian populations are kind of small scale compared to some of what we've seen in other planetary systems. And then there's a lot of complex structure in the semi-major axis distribution of the cold classical Kuiper belt. And what is that telling us? So one idea, there's this kind of overdensity that we call the kernel, kind of in here. And maybe that's related to a jump in Neptune's orbit as it's migrating, due to perhaps that ejected ice giant that's been proposed. So there's a lot of kind of fine scale details here. All right, so continuing our inward march in the solar system, the next related icy body population are the Centaurs and then the Jupiter family comets. So all those dynamically hot populations in the outer solar system, the ones that do have Neptune encounters can enter the giant planet region, where they have lifetimes of 1 to 10 million years, and then some of them will make it all the way into the inner solar system to be the short period Jupiter family comets. So up here is kind of a typical example evolution where you have something out in the trans-Neptunian populations where it's stable for something like a gigayear. but these just kind of long time scale gentle perturbations gradually increase this eccentricity until it encounters Neptune. It'll spend something like 10 million years scattering around the scattering population, and then enters the giant planet population for something like 10 million years, and then enters the inner solar system for maybe 10,000, 100,000 years. And these are just some examples of the dominant dynamics here. So these are some example centaur evolution tracks where we are in perihelion versus aphelion space now, to kind of show that these are some examples where you're kind of handing off objects between the giant planets. So you have something interacting with Neptune, and it starts interacting with Uranus, then Saturn, then Jupiter. And then, this is easily modeled. These dynamics are just dominated by planetary scattering events. So we have pretty good models of the distribution you'd expect in the giant planet region. So this is just a time-weighted map of the centaur population. So the longest part of the evolution is happening out kind of between Uranus and Neptune. And then the timescales get shorter and shorter as you go in, because you're encountering the more massive planets. The orbital periods are shorter. So you get to very fast timescales as you come in. So some really interesting parts of the centaur population is how many of them are active. I think that was perhaps unexpected. So this is a snapshot of the scattering centaur and Jupiter family comet populations here, again in perihelion, aphelion space. And the triangles are all of the centaurs that we know outgas or outburst, have some cometary activity. And you'll notice that some of them are on orbits that go pretty far from the sun, and yet they are still active, although most of them do have perihelion distances kind of inside 15 AU. And this was noted, a while ago. So Jewett 2009 was the active centaurs paper. And at the time, here were the perihelion distances of the active centaurs compared to expected mass loss sublimation curves versus distance for common volatiles in the outer solar system. So the thing of note here, water, which is the thing that drives most of the inner solar system cometary activity, just doesn't really matter outside of Jupiter's orbit. It's just not enough energy to have significant sublimation there. So it must be some of these other volatiles, carbon monoxide, carbon dioxide, but even there, the energetics don't quite explain some of the vigorous activity we see. So there's a lot of work to be done here on understanding the activity. Kind of one of the things a lot of people are looking at right now is whether phase changes in water ice can be providing the energetics for some of this activity, amorphous to crystalline water ice, because the activity can be extremely vigorous. So this is the most active body in the solar system, 29P SW1. And this is magnitude on the y-axis. And I just want you to note it goes from 10 to 18 down here. And this is its brightness over time due to having these massive outburst events. So it'll sometimes brighten by many magnitudes at once. So it's just an incredible amount of activity. Now, this is also a close-in centaur. It is just outside of Jupiter. But there's a lot to be learned about what's driving this activity. And of course, what drives the transformation, we now have this beautiful picture of Arrokoth. It's a cold classical Kuiper Belt object, which is not part of the hot population that really drives the majority of the Jupiter family comet and centaur population, but it's the only small body image we have from the trans-Neptunian region. But you can kind of see the dramatic difference between this and 67P in the inner solar system. So there's a lot of physical evolution that happens to these bodies, and they're our best chance at getting direct chemical observations of that early planetesimal disk. But we have to understand this transformation that happens to interpret everything. And clearly it starts in the centaur region. So I'll just highlight, LSST is going to give us a lot more centaur observations. It'll also give us a bunch more comet observations. There's just not nice plots to show. So this is from a recent estimate of the centaur yield from LSST. But I'm gonna go past that. I'll just note the Jupiter family comets are cool. I don't have as many plots on that. Kind of the interesting thing here, we know their dynamical lifetimes are longer than their physical outgassing lifetimes. That's kind of the big thing with the JFCs from the dynamics standpoint. If they stayed visible for their entire kind of 10 to the 4, 10 to the 5 year dynamical lifetimes, the inclination distribution would be wrong compared to the observations because they last long enough to constantly get pumped up. So we know they have to kind of turn off at some point. And again, that's part of the physical processing. So there's a lot to be studied there to really understand this transformation and connect all of our lovely comet spacecraft data to some of our outer solar system spacecraft data. So, we have the New Horizons data. Hopefully we'll have some comet interceptor data. We'll have Lucy data soon, so I'd barely mention them, but the Jupiter Trojans are perhaps thought to have formed in that same planetesimal disk with all of the things that became the trans-Neptunian populations in the Oort cloud, but they've been sitting at 5 AU for 4.5 billion years. So understanding that transformation is important. So, we've got this tangled web of small body populations, and I'm just going to briefly fly back through what I think are some of the interesting questions since I have my 1 minute left. For the outer part, the most distant primordial populations, I think it's going to tell us a lot about what were our interactions with other star systems, other planetary systems. Is Oort cloud formation common? Are we hosting exocomets in our own solar system? A little bit closer in, the TNOs are going to tell us a lot about planetesimal formation in our solar system, which of course hopefully tells us something about planetesimal formation in other planetary systems. The size distribution of what forms, what sets the edges of these disks as they form. And then the innermost bodies are telling us about the physical processing. And of course, we get the most detailed chemical observations from these inner solar system bodies, but they also require the most complicated interpretation because they're not really pristine anymore. So I will end on that and take any questions. Thank you.
Great. Time for a question or two.
Hi, Kat. Awesome talk. I actually had a question about the edge of the cold classical belt. So you said something that intrigued me. So I want you to put on your speculation hat and tell me what does it imply about the formation mechanism if it turns out that the cold classical picks up again at like 60 or 70 AU and keeps going?
Then we have a gap to explain. I think that would be cool.
Yeah.
Because then we got to figure out why there's a big gap in the population because it really does drop off. There's a little bit of colder things past the 2 to 1. But yeah, then I think we'd have to be really thinking hard about why was there a gap. But yeah.
Yes, let me echo that. Great talk. 2 things from New Horizons that bear on exactly what we were just talking about. One is that our ground-based surveys in search of a new flyby target in the Kuiper Belt have yielded the detection of an anomalous number of very distant KBOs, all beyond 80, I think 75 or 80 AU. It's not a very large sample, and it is only along one line of sight. Wes Frazier and company published this result. And interestingly, they're only beyond that distance, so that may also be speaking to the gap.
Yeah.
However, contrary to the gap, the New Horizons spacecraft carries a dust detector, which expected to see a fall off in dust density as we went over the 2 to 1, and we didn't. And we're now 20 AU past that, and we're still seeing constant or even slightly rising rates of dust impacts, which is super interesting.
Yeah, and I forgot to mention one of the cool resonant populations, which is the 5 to 2 at 55 AU. And it is really strongly populated, and we don't quite understand why, because there should have been no cold disk for it to sweep up during migration. There's not been a satisfactory explanation for why the 5 to 2 has so many things in it in our current kind of models. So maybe these are all telling us that we don't know the story. The cold disk is really hard to see. Low eccentricity orbits past the 2 to 1 are very hard to see.
Okay, I think that's all the time we have. Let's thank our speaker again.
Thanks very much.